All right, so we hadn't quite finished the CD section last week, and so that's basically where we're going to pick up. It's so you got copies of the newer edition of Van Holt Johnson Ho, and occasionally I steal stuff out of there, or I use those figures, or I use those chapters. Sometimes they're better chapters, sometimes they're way more complicated. So one of the things that's different about the new book is Johnson and Ho bring different things to the table than Ken. And so Johnson's basically a spectroscopist. He's known for his CD work. He created a lot of the methodology that's used in the modern analysis of CD spectra. But the book is written from a quantum mechanical perspective. And so there's introductions to quantum mechanics, and the older, shorter books by Ken, that was all glossed over, and they reference you to another textbook. This book basically covers it, not quite up to the same level as a chemistry quantum course, but and so reading a lot of those chapters makes it a little more challenging, to say the least. Okay, and so historically I have avoided covering that in this class, but they've also expanded a lot of the stuff in their various chapters. So the CD chapter, for example, is greatly expanded, especially the section on nucleic acids. And there's a lot more detail in analysis of protein CD, how you actually go about doing the analysis. They give you some of the methodology, some of the mathematics that goes into fitting data, which I'm going to talk about, but I'm going to talk about it vaguely. And so I think at the end of the 10 or so slides we're going to talk about, I'll reference some of that, and I'll pull up the book and show you explicitly what I'm talking about to have to make the point. Okay. You do or don't appreciate or know that when I do this, I spend a lot of my time reading other stuff that I'm not presenting to you, but that I'm presenting to myself, if you will. I could be doing it this way, and I look at other books, I look at other papers. So I've spent this past week time reading the CD chapter out of the other edition, but I also have read the quantum mechanics chapter, and I'm in the process of reading one of the other spectroscopy chapters, etc. And so I'm always looking at other other things that I could be doing, and this is all from the perspective of a Van Holt book. There are other textbooks out there that I allude to in the syllabus that do things in a very different way, with a lot different details, covering the same kinds of things. Not all biophysics textbooks do methodology the way that the Van Holt textbook does methodology. And so there's a lot of different ways of doing it. And so I'll say at the end of the lectures today, the next topic that we cover next week is going to be electrophoresis. And sometimes I use the old chapter, but I definitely can see that I should be using the new chapter out of the new edition of Van Holt. And so that's what we'll be using. I posted what I think is called chapter 6 in the old book, and it's now chapter 5 in the new book. I posted chapter 6 in Canvas, but chapter 5 you have access to in the full edition of the physical biochemistry, I think is the title of the book. Is that right? Yeah, well, it's labeled here as physical chemistry. And so for the electrophoresis, we'll do that next week. I usually fill in the details using papers. I specifically will have you read 3 papers, but we'll talk about this in a little bit. Okay. So let's start with circular dichroism. Where are we? Here. All right, and so we were talking about optical rotation and talking about the way that light interacted with asymmetric centers or certain kinds of asymmetric optical properties of helices, etc. And we talked about positive dextrorotatory and negative levorotatory or clockwise and anti-clockwise rotational light. Okay. And then I hit this slide and I said we would stop and we'll come back to it. So I made the point when I stopped that the whole introduction, and the reason that it's based on quantum mechanics, the whole introduction to spectroscopy in a molecular biophysics class emphasizes the duality of particles, the fact that they can be thought of as particles and they can be thought of as light. And we can think of the interaction of light, electromagnetic radiation with macromolecules in terms of the properties that lead to light scattering. Why is the sky blue? Or properties that lead to wavelength dependent spectroscopic transitions that have something to do with the fact that light can be absorbed. Okay, and so it continues to be those properties. Optical rotation is a reflection of different refractive indices, as this figure legend says, and it reflects the fact that
Dr. Correa,
yeah.
are we supposed to be looking at a PowerPoint?
Oh, did I not share the screen?
I don't see one.
Ah, thank you very much. Some people just like to talk. There we go. Better? All right, sorry.
Yeah.
I started the
I didn't even realize that you were supposed to share the PowerPoint. I was just listening to you.
well, that's one way to learn.
Yeah.
They're used to, you know, imagine lectures hundreds of years ago that people used to go and listen to. There were no transparencies even. People just stood up and talked.
Still same in some parts of Nepal in my country. Like there's no PowerPoint or anything. It's just listening to the teacher talk. Yeah.
I'm sure that's true in lots of parts of the world.
Yeah.
You might think of this as lots of cultures, especially in places like Africa, where people tell stories, and you know the history of your people from the stories that you tell, and your connection to your culture is through the stories that may be thousands of years old.
Yeah.
I don't know that that's the best way to learn biophysics, but it's certainly one way. All right, so let me go back. So this is where we were last week, and I was finishing up this notion that asymmetric centers can be either positive or negative in their interaction with polarized light, and it can cause the light to rotate either to the right or to the left, clockwise or anti-clockwise, dextrorotatory or levorotatory. And this depends on the symmetry of the asymmetric center. You learn this in chemistry by putting the smallest molecular weight in a tetrahedral structure in the back, and then you ask, do the molecular weights of the constituents go clockwise or counterclockwise from smallest to largest? And this is sort of a way of thinking about that in terms of a simple asymmetric carbon. The light interacts with all kinds of asymmetric characters, and so it will necessarily have some kind of asymmetry that will cause the light to be rotated. The specific rotation, the magnitude of the specific rotation will depend upon the actual characteristics of what that asymmetry is. Okay, and so asymmetric centers like a carbon is different than asymmetric centers like a helix. In principle, it's the same phenomena. Okay. And so this is sort of a light scattering phenomena. The emergent light is still plane polarized, but the plane has been rotated. So this is still a wave that has been rotated. Okay, and so the optical rotation matches the wave properties of the light. The circular dichroism results from a difference in absorption of left and right circularly polarized light. And so this is the absorptive property. In a quantum mechanics sense, this is activating a transition from one energy level to another energy level. We went through that in the absorption part of this lecture. Are these vibrational modes? Are these electronic modes? Are these rotational modes? And the energies are all different, but you can induce transitions from one energy level in a ground state, for example, to another energy level in an activated complex. So these are absorptive properties. The optical rotation results from this difference in the refractive index of the L and the R, but then you get an absorptive property. And so all of this language up here is emphasizing that. Absorptive bands, there are differences in both absorption and refractive index. And in principle, you see that in the comparison of the spectra, although the magnitudes of the bands may not be as great. There are lots of different ways of reflecting circular dichroism strength. Often it's done in these units of delta epsilon and some fractional delta epsilon. They're making the point here that these are very small changes. And so you need very, very precise instrumentation to be able to see these measurements. The example here is showing you how they are comparing left and right circularly polarized light. They're making this by the different techniques that are discussed in the previous slides. And if they have equal magnitudes, then you will see a response from one or the other, and the rotation that you get will reflect the projection of each of these axes onto the average, or the sum of the left and the right projections. And so this is a rotation that you will see in terms of an optical rotation. I'm just reading the text down here. Okay, and so this is the rotation that occurs in that example up above when you have equal left and right circularly polarized light magnitude. And so that example, the polarized light is being generated by equal components here. But then if the different components interact with the molecules in a different way, then you'll get a rotation that reflects this new projection. The examples that they give here are sort of simple and meant to be sort of obvious where the optical activity comes from. Here's an example of two different ring systems, one of which is symmetric and optically inactive, and the other of which is asymmetric and optically active. Okay, it makes the point here that plane and symmetry, it makes the point here that racemic mixtures have no optical activity. That's the point I made at the end of the lecture once I had stopped the slide with L and R amino acids. And this would be true of mixtures of left and right helices, although you usually in macromolecules don't have mixtures of left and right helices. You generally get left-handed helices or right-handed helices. You know, or maybe you don't know, but if you make proteins with L amino acids, then the helices tend to be one way. They tend to be right-handed, and we should verify that I just said that correctly. But if you made it a protein with R amino acids, you could make up a synthesis system where the R amino acids are provided. The enzymes might not work very well because they're used to left-handed helices or left-handed amino acids. But if you could make up a protein with R amino acids, all of the asymmetric centers would be the opposite helicity. The helices would go in the opposite direction because the R's symmetry in the amino acids would naturally tend to make the wrong or the opposite mirror image, if you will, of the helices. I can't remember the name of the guy at Southern who was actually working on this for a while. And this is a common observation. People experimentally have done this, okay? And so this is simply showing you an easy indication that symmetric molecules will be inactive, asymmetric molecules will be active. And so this asymmetric molecule, hexahelicine, will have both optical activity for rotating light, and it will also have a CD spectra. Okay, and so it gives you a window into that asymmetry and something about the structure. Okay, the strength of the interaction depends upon interactions within the asymmetric center. Between the electric dipole moment or the transition dipole moment and the magnetic dipole moment. So when you have an electric vector in a polarized light, it naturally induces a magnetic vector, usually at a right angle to it. Okay, and the interactions that are occurring in the molecules that we're talking about involve transitions in electronic interactions with the E vector, but also magnetic interactions that exist in the helices themselves. Okay, and this is pictorially showing you that the magnetic field will also interact with the molecule. Now, this is showing E1, E2. This is showing this must be in the text that I'm not remembering. This is showing you two electric vectors, both of which can be interacting with the molecule, and that there's a magnetic vector associated with it that is also interacting with the molecule. Okay, and so the rotary strength, the magnitude of the CD signal that we're going to be measuring depends upon the angular dependence of this interaction. In the earlier spectra, we talked about, I think in the nucleic acid examples, we talked about the fact that if you line up all the molecules in some way, shape, or form, they describe things like stretching, or in one of the polybenzyl glutamate examples, the helices had this natural tendency to line up anyway, and so you could shine the light parallel or perpendicular, and you would get different strengths depending upon their interactions with the strengths of the vectors, the electronic vector and the magnetic vector in the helical character of the molecules themselves. Okay, and so it's this angular dependence at what is it lined up or is it perpendicular? And therefore the cosine of the 90-degree would give you 0 interactions, or you could get some kind of a maximum interaction. And so that's what this is meant to depict. Okay, I don't remember what the E1, E2 actually is referring to here. Okay, so I alluded to a lot of this, and this is where we're going with this, that there are 3 kinds of asymmetry that we generally talk about. One of which is that 19 out of the 20 L amino acids have an asymmetric carbon. So that's one source of the asymmetry. A second source is that many of the secondary structures in proteins have an asymmetric nature. So if you have an alpha helix, that alpha helix will have a certain interaction with the CD, with the circularly polarized light, and you will see that. It doesn't have to be just alpha helices. The beta sheets will also interact with the CD spectra and will give rise to a specific characteristic structure. And then the tertiary structure of the various units in a protein, combination of the carbons and the other structures, may also have or give rise to some kind of an asymmetric environment. This is generally thought of, and I think the book is making the point that this has to do with the asymmetry of the environment of the amino acids, for example. So there are, and I'll say this when I get to a CD data set in a few moments, that we look at alpha helices, beta sheets, random coils below about 250 in the spectra. Above 250, we tend to be looking at environments of amino acids. We primarily are looking at tryptophan, phenylalanine, tyrosine, and that is the asymmetry that this third point is sort of referring to. The fact that the tertiary structure creates an asymmetry in the environment around the tryptophan, for example. And that's what you actually see in the CD spectra. I think none of the data that I'm going to show you is going to reflect this. They tend to be much smaller signals, so they have a much smaller rotary power. And I'll discuss that when we get to those figures. In this particular example, they're showing you dimers. So dimers of a ring where the electronic transitions are coupled to one another. So this is another characteristic that reflects sort of the helical character, that light will interact with these structures in a slightly different way because of that angular dependence, that cosine dependence. And if the rings are parallel, but rotated with respect to one another, then the interactions with the light will be different. Okay, and so orientations that give rise to polarization that sums, which as opposed to polarizations which cancel, may give and probably do give rise to very different CD signals. Okay, and so this is the asymmetry that you're becoming sensitive to. And so what I want you to appreciate is, I'm saying this in sort of a backwards way. In terms of the spectra that you collect, the reason you do the CD is to discover something about the orientation of these structures. Okay, and so you get a CD signal, or you don't get a CD signal because of the asymmetry. And so it gives you information about the asymmetry. If you don't see the asymmetry, then you know that there's some symmetry in the structure. And so it gives you information about the different kinds of asymmetry. Okay, and that's sort of what you're interested in. The fact that it's a dimer, and this goes back to sort of the quantum mechanical character of this. For a dimer, there's a splitting of the transitions into two bands. This splitting has something to do with the transitions that are allowable. And so you get transitions that are shifted relative to the sum. So this is the difference between the left and right circularly polarized light that we're talking about. But there's a splitting quantum mechanically that give rise to two different bands. And what you see is the sum of the two bands. And so you can see the dotted lines, okay, sum to give the solid black line. All right. And you can see there's a shift in the wavelengths, and there's also a shift in whether it's positive or negative. And that's what gives rise to the sum. And so it's this splitting that occurs in the simple molecule like a dimer. You can imagine that this being multiplied n-fold when you have n-mers in a helix. And so that's what you get. You get this summation of two different structures. And you get the negative positive because the differential nature of the absorption, that the left and the right circularly polarized light are now absorbed in an opposite way depending upon the arrangement of the dimer. Okay, and so this is sort of a fundamental feature that you see. Now, the real application, there are lots of people who use CD for small molecules and for other kinds of applications. The real application in protein chemistry is to look at the CD spectra to learn something about the nature of the polymer. Okay, and I said protein, but this actually is referring to an RNA. But it's learning something about the polymer. And the point of this slide is that there's a difference between monomers, dimers, and polymers. And so C is the CD spectra of a monomer, and it's a very small signal. The minima is somewhere around 250. Okay, and so there's asymmetry, but there's not a lot of asymmetry, and it doesn't interact very strongly with the light. Okay, and we've already talked about this in general. The dimer is this signal, and it has the features that I just showed you, where it has a shift relative to the monomer. There's this enhanced negative positive band. Okay, so that you've already made an oligomer, and that the oligomers, the monomeric units in the dimer talk to one another, couple with one another, is the way that they used it in the slide back here. The electronic transitions in the two rings are coupled to one another. So the electric magnetic vector here is sensing the electric magnetic vector here, and that's the cause of the coupling. Early on, we talked about how distance could be measured in fluorescence. Well, this interaction is close enough that these electric and magnetic vectors will interact with one another, sense one another, and you'll see that in the signal that you get. And so that's why the dimer gives a much bigger signal than the monomer, because you now have this coupling between the electronic and magnetic vector that is interacting with the light. Okay, and often when people work in this business, they put stuff on a per mole of base. So you wouldn't just say per monomer per dimer, you would say per base. Okay, and so the dimer has two bases in it. And so you would correct the data for the fact that there are two bases in it, but even corrected for the number of bases, you can see that there's a much bigger signal here. All right. The polymer gives this much larger signal. This is spectra A. Okay, and then so that's part of the point of doing this experiment. The fact that the polymer has a much bigger character. Even as a RNA, which is single-stranded, the bases along the chain are sensing one another, and they have some helical character that is big enough to cause coupling between all of the bases. It's got some random coil character, but it also has some stacking interactions that reflect this coupling. But the coupling is long range now because it's across many, many bases. And so you get this enhanced signal. And again, remember that this delta E is per mole of residue. So A is the equivalent of reflecting for one base. This is the magnitude of the signal. But if this RNA is 500 bases long, this signal is actually 500 times larger than the signal in B and C. Okay. And so it's reflecting the coupling and the magnitude of the coupling in the asymmetric units in the RNA molecule. So it uses the term greater qualitatively different. Qualitatively different reflects the crossover, where it crosses over. It reflects the magnitude of the peak and the minima, what wavelength they occur at. So notice relative to the dimer, they're all shifted. They're all shifted downfield. Okay, so at a slightly lower wavelength than the dimer, and which is at a slightly lower wavelength than the monomer, and that the crossover also changes. So this crossover point also becomes a big factor in interpreting some of the data. Okay. So this figure then goes on to say, okay, that was for RNA and single strand. What if we have double-stranded DNA in this case? What can we use it for? All right. And again, the CD is useful and is used a lot by the nucleic acid guys for looking at the conformation of the bases. Okay. And so in this particular example, we're looking at B form, the solid symbol, and Z form, the dotted symbol DNA. And you can see quickly that these two spectra are different from one another. This actually is data from one of the authors of the big book that we're talking about, Curtis Johnson's book. And so you can see the difference between B form and Z form DNA. Okay. The structure, and this is just poly DGDC. And notice it's poly DGDC that is a right-handed double helix. And so I'm guessing that this is a GC, 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 GC sequence that can then anneal to make a double-stranded, slightly aligned by a base or so, and anneal into a right-handed double helix. Okay. Notice what causes this transition. It's caused by salt. So in concentrated salt solutions, a transition occurs to a left-handed helix that is called and known as the Z form. Okay. It's not a perfect helix. It's an inversion of the structure. So notice suddenly what was a peak becomes a minima, although it has other interesting characteristics that are different. And so you can study Z versus B and the transition between B and Z by doing CD. The inversion is not exact as the language that they use, because Z is not just a left-handed B form DNA. It has lots of other differences in its backbone, alternate base stacking, alternate hydration. There are lots of differences in Z form DNA. But the power of CD is that you can see this, and you can see this easily, and you can study this transition. What's the temperature dependence of it? What's the salt dependence of it? What's the kind of salt? Because it will be sensitive to sodium and potassium and lots of other features. Probably the pH dependence of it. There are lots of different features that can be looked at. Okay, so the easy thing is low and high salt concentrations, low and high ionic strength, or low and high concentration differences. Okay. So they use the terminology here, and I'm trying to emphasize this, that it's a tool for studying these conformational transitions. As an aside, and you should give me feedback about this when we reach the end of this series of lectures, the series of slides. ZDNA was a big deal when it was discovered in the early 70s, late 60s, whenever it was discovered, because people didn't quite know what it was good for. It's just some weird laboratory observation. Or is it real? Can we see it in cells? And does it have a function? And what is that function? Okay, it was a big deal when somebody actually finally saw it in cells. It was done antibodies to ZDNA, and you could see reactions in the genome of certain cells. And then the question was, gee, where is it in the genome, and what's, again, its function? What's it doing there? The discussion was curious because one of the arguments was that ZDNA doesn't exist, yet you only see it when you induce it by adding an antibody that binds to it. So the antibody is causing the ZDNA, otherwise we don't have ZDNA. And so I think this argument continues to this day. People aren't entirely sure what ZDNA does, and there still continues to be this question. And I'm guessing that in cell biology, when you take cell biology, and I think all of you have had it, maybe one of you or so have not had cell biology yet, you don't discuss it a lot. Okay, it's not emphasized a lot in textbooks because it doesn't have great functional value relative to lots of other features. So correct me at the end if I'm wrong about that. Okay. Now, that's a little bit on nucleic acids. And as I say, in the other version, which is in the textbook, there's a lot more examples of the difference in the CD spectra of bases, the monomers, the CD spectra of different kinds of structures. Over there, they compare A form, B form, and Z form, and lots of other things that the nucleic acid guys have used it for. There are lots of other nucleic acid structures that are out there that people are interested in. And a lot of those structures have been characterized by circular dichroism, and they deserve their own sort of day in court, if you will, but this version of the book doesn't talk about them a lot. You can read a lot more about that in the other version. This department used to have nucleic acid biophysicists in it, and we would discuss this stuff in a lot more detail in the normal course of seminars, etc., in this class. We used to have a nucleic acids course that went away when that faculty member left. Okay. So for proteins, there are also characteristic features that you see by circular dichroism. And so remember I said below about 250, you can look at secondary structures. This is the vacuum UV absorption spectra of that benzyl gamma, polygamma benzyl L-glutamate in an alpha helical conformation. Again, this is from Johnson back in the early 70s. It's vacuum because once you get below 190 or so, oxygen absorbs a lot of the energy. And so you have to do these CD under conditions where you pull a vacuum so the beam isn't going through the oxygen. It's not the oxygen in the sample, it's the oxygen in the path that the light has to traverse to get to the sample and then to go to the photomultiplier. So you basically have to suck all the oxygen out of the experiment. In a typical CD instrument, we used to have one here. The one I use now is either at Millsaps or at the other school where Reed Bishop is across the street from here at Bellhaven. And what we do is we flow nitrogen through the chamber and down the optical tract to reduce the amount of oxygen that's in the air and to be able to get even down to 190. Curtis Johnson developed this method of going all the way down to 140, which gives rise to more peaks and more information in the spectra. And so what you can see is that in a typical alpha helix, we have these two major minima, one that occurs around 220 and another one that occurs around 208. And then there's this characteristic peak that occurs around 190. Often it's very difficult to get to even 190. And then there's these additional features that occur at much lower wavelengths, this minima at 160, for example. This is showing the equivalent absorption spectra. And so in a typical absorption spectra, the main thing that you see is usually out here around 280, where you see the tyrosine tryptophan environment. At these wavelengths, what you're primarily looking at is the backbone. And so this signal down here around 200, we don't usually do absorption spectra down around 190, 180. But this is what this signal is coming from. And so these are what the transitions are that are contributing to the CD spectra. And so these are secondary structure elements. There are 3 of them that are discussed here. The one at 210 to 220, this stuff right here, are what are called N to pi star transitions, in which a non-bonding electron of the carbonyl oxygen are promoted to an anti-bonding pi orbital. Okay, and so this is quantum mechanics speak for the kinds of orbitals that exist around various atoms. This is a weak transition, and so you see that here in the absorbance, but it can play a major role in the CD spectra, and that's reflected in this double minima here, okay? There's also a strong pi-pi star transition centered around 190, and so that's what gives rise to this peak. And then below 180, the structure of the peptide is less well understood, they say, but it's also some kind of a pi-pi star transition that occurs around 160. Notice the minima. And so that's why I emphasize here in my language the fact that there's a vacuum here. And so seeing the fact that it's in an alpha helical structure pops right out at you. This 220, 208 minima tells you that there's alpha helix in this particular model compound. Okay. Model compounds are great. They allowed us to assign various things to the CD spectra. But what we really want to know is what is the fraction of secondary structures that a protein might exist in. So this is another model compound, poly-L-lysine, that can be induced to go into an alpha helix or a beta sheet or a random coil. Okay, and so it shows you the features that can be described as alpha helix. Notice the 220, 208 minima, or beta sheet. Notice the single minima around 215, 216, often described as 220, or the the random coil, which is this structure, which has this minima down here around 195, 196. Okay, so it has this slightly positive structure around 220, and then it has this major minima down around 294. And so you can see that if they existed alone, you could immediately pick out alpha helix, beta sheet, random coil. All right. So when I do CD in recent years, I tend to do it on an intrinsically disordered protein that we could call random coil. It's not exactly random coil, okay? And the feature that we look at is this 195, 194 minima that my protein exists. This is the ELP that Drozen works on, the ELP that Lee Bidwell works on. Okay, and that my lab has worked on and still does some dabbling in. All right, and so you can see it in intrinsically disordered proteins. Okay, if you had a protein like hemoglobin that was 100% alpha helical, this is what you would see. And if you had a protein that was entirely beta sheet, some kind of a beta barrel protein, some kind of a membrane protein that somebody like John would talk about, you would see that in the structure. Okay. So this is sort of a take-home message. This is what secondary structures look like. However, typical proteins are mixtures. They're not just alpha helix, beta sheet, random coil, okay? And so the challenge is looking at a CD spectra. Here's an example from Curtis Johnson again, where he's trying to figure out what's in this protein. All right. And the way that he's doing that is he's fitting the CD signal to what he calls a basis vector, where you have characterized a series of proteins by X-ray crystallography, and from their X-ray structure, you know what fraction they are: alpha helix, beta sheet, usually some kind of a beta turn, and random coil, and then fit the unknown spectra to a sum of those CD spectra that reflect a certain fraction. Let me see what I have here. Okay. So what I mean by this is, here is cytochrome C by X-ray, and here are the various different structures that exist. Okay, so it's 30% helical. It's no percent anti-parallel. It's no percent parallel beta sheet. There's a bunch of turns, and it's mostly 45% other. Other meaning probably disordered. You then fit that data with a basis vector from, let me look ahead here. Oh, that's the last one. Okay. With a set of proteins, for example, elastase, hemoglobin, lactate dehydrogenase, papain, you can see exist of different amounts of helix, different amounts of beta sheets, different amounts of turns. And what you do is you ask, if we fit the CD spectra of cytochrome C with the CD spectra from some other family of proteins, and I do a linear combination of them, can I get back the right answer? And you can see that the CD spectra is close, 42 versus 38, 10 and 10, 68, 75 in the helix column, but not perfect. And so what this figure is showing you is how this method is done. You might try to fit it using, so this is trying to fit the CD spectra of papain using 1, 3, or 5 basis spectra. The basic spectra would be from proteins like this, and they would correspond to these CD spectra, but we can assign them values, the helix, the sheets, the turns, based upon their X-ray structures. So we know in absolute terms what the right answer is, but the CD spectra does not give back a perfect right answer. Why is that? Well, the reason is that the alpha helix in one protein is in a slightly different environment than the alpha helix in other proteins. And that slightly different environment changes the coupling, changes the shape of the spectra, changes the way that the circularly polarized light interacts with it. So you get a slightly different answer. Okay, and so CD is notorious for being a little bit imprecise. It's really obvious when you have a double minima that you have some alpha helix. The question is how much alpha helix and how much beta sheet is hidden behind that spectra. Because remember, the beta sheet spectra has kind of an overlap. It has a minima around 220, but it overlaps with the alpha helix. And the random coil has a positive going peak in here around the same place. And so you're trying to resolve all of that to be able to do this sort of analysis. Okay. And that is the end of this. So let me stop this for a second and show you that in the other version of all of this, they go into a lot more detail. Sorry. So here is a structure, an example of an alpha helical protein, calmodulin, and its alpha helicity is calcium dependent. You know that calmodulin binds calcium. And so it induces alpha helix as you add calcium. All right, and so you can see changes in the minima. Notice this minima is not exactly at 220, and so that's part of the problem, that these things move around a little bit, and that the magnitude of the peak at 190 changes. Okay, and so it's the same protein, changing conformation, having more or less alpha helix in a calcium-dependent way, And you can start to sort of study that in various ways. Okay, but the question is, what are those subtle differences? He goes into a lot more detail on how you fit the data in this chapter, which I'm not going to do with you, but he's showing here that you can do this calcium dependent analysis and look at the differences in the CD spectra. Here is the way that you sort of have these wavelength dependent spectra that you're using for the analysis. This is actually in analyzing DNA, but you can do this as well for analyzing protein. And they go into all of the different things that you can do. And it's down here where we get into the sum of different kinds of spectra. And so this is a repeat of that figure that I was just showing you, using 1, 2, 3, 4, or 5 basis vectors. The weird thing that you do in this analysis is you might use a set of 5 basis vectors to fit data, and then you refit it with a completely different set of proteins, and you fit it again and again, because different combinations give slightly different answers. And so this is going through the full mathematics of this. And so here are the examples of the basis vectors and what fractions of helix they have. And then you look at the various signals in the CD spectra and you fit the unknown with this matrix of wavelengths to get back the kind of right answer. Okay, and this is showing examples of predictions from this type of analysis. Okay, so I think that that's enough detail without trying to go through all of it. Okay. So let me bury this guy. Let me not stop. Yeah, stop sharing. All right. So that's the end of the CD topic. Now, I asked a question while I was lecturing. What did you learn about ZDNA in the cell biology class? And it may be just Ahmed who has not taken our CD class. I think the rest of you have had it. Am I right about that?
No.
Oh,
not
so Sarah and Jelena, you haven't had it yet? You take it next year?
We
Okay.
just took medical biochem last year. That's about it.
And what have you learned about ZDNA in your previous biology classes?
No.
Nothing.
Yeah.
Okay. And cell biology doesn't talk about it either?
I don't remember much from it.
Right. Okay. And so that was my point. So I wasn't wrong. Believe me, it was a really big deal. I don't think somebody got a Nobel Prize for it. I don't think it went that far, but people were very excited about it in the 70s and the 80s. And the argument continued well into the 80s. I remember this still being a topic in the 90s when the antibody work came out. I think it came out in the 90s. Maybe it was in the 80s. And then you don't hear about it because nobody has ever figured out what the purpose of it is, what the function of it is. There's probably somebody who will correct us and say, no, so-and-so has shown this. But we just basically don't know what left-handed DNA is for. All right. I appreciate there's a whole field out there of people who work on unusual DNA structures. Okay. And these unusual DNA structures are usually single-stranded, not always. And they usually exist in certain kinds of base compositions. So you have to have C-rich DNA, for example. And as a single strand, it will make some kind of a structure. And that structure is an interesting lab tool, but it may also have some interesting application. And if you can induce a piece of DNA to unfold in a search section, 100 bases that unfold into 2 single strands, and then they fold up into something else, okay? They may be targets for drugs. So for example, if you had them at some kind of start sequence for replication or start sequence for transcription, then you could actually shut down the transcription of a gene. Okay, and so if you could induce that to happen by a drug that binds to a particular kind of single-stranded structure, then maybe it can actually cause transcriptional regulation. Okay, there's a lot of evidence for this, and people are trying to develop drugs for that very purpose. All right, so you have a gene that's inappropriately expressed and you can shut it down in principle. So what you do is you end up studying the single-stranded region, and you study its salt dependence, its temperature dependence, et cetera. I've been collaborating with Randy Watkins up at Ole Miss on a project for a number of years, and we've published some work on this, and we're still writing papers actually that Randy is working on in C-rich structures. Do they exist in nature? Can you induce them to exist? Are they actually used for transcriptional regulation is the question. I think there's no doubt that you can induce them. There's no doubt that they might play a role. Is it a way of going for regulation, and can you make effective drugs is the continuing challenge. Okay. There's a whole field out there of I'm not going to use the right word here because I'm going blank. There's a whole field out there of using DNA to build structures. Okay. What kind of structures? Knots. Literally, you use DNA to make a box. Okay. You can imagine a cube. What's at the corners of the cube? It's some kind of a junction that goes in different directions. That should remind you of a holiday junction. You all know what a holiday junction is. Okay. And so you can imagine that somebody designs a sequence that at a junction makes double-stranded structures, but then it changes direction because it now is annealing to a different strand, and you suddenly have a junction, but you don't have one junction. You have 4 junctions that'll make a square. You have 8 junctions that'll make a cube. So you could literally use DNA to make a cube. Why would you do that? Well, because it sounds curious and interesting and neat. Okay, it's like being an artist, except with DNA. How do you prove that you've made it? Interesting question. Can you see it? Literally see it? Could you run it out on a gel? We'll talk about this next week, and observe a particular size and shape that is consistent with it? Can you do CD on it to pick up the kind of characteristics that you would expect from a double-stranded structure, but that is cube-like? That might be more difficult to imagine how you would come up with model compounds. What if you don't make a cube? What if you make a lattice? What if you made a 3-dimensional lattice of cubes? You could imagine a lattice where all of the strands have joined together in a way that it looks like knitting, except it has dimensions. It has a 3rd dimension, not just a 2nd dimension, where it's a sheet of lattices, a sheet of squares, but it's a sheet with a depth of cubes. What if you could do that? Would that have some purpose? Maybe you could. Yep.
That sounds a lot like nanocaging, like, but you know how some people are using ELP molecules to nanocage drugs and other and antibodies and everything.
It is, except on this level, it's a far bigger nanostructure.
That's interesting.
Okay? But exactly right. Okay. So you might or might not be familiar with this. We'll have to go looking for the papers. What if I wanted to use DNA to write a message? I literally want to use DNA to write the word down, DNA. You can actually do that. You can actually design a sequence that will form a double-stranded D and a double-stranded N and a double-stranded A, and you can visualize it by electron microscopy. What if I wanted to make a structure that made a smiley face with DNA? You can do that. People have done that. Okay. You have to design the sequence very precisely so it falls up in a proper way, but you can do that. All right. The Nobel Prize 2 years ago, 3 years ago, was given for the people who are doing this kind of nanotechnology with DNA. All right. A friend of mine created this field. He actually started working on this in the 80s. His name is Ned Seaman. His name was Ned Seaman. Unfortunately, Ned passed away this year. He died of long COVID. Ned has been at NYU for 40 years, and he caught COVID early in the outbreak in New York, and he never got better, and he eventually passed away. Ned was 75. He did get a different award. It was also $1 million prize. It was a different Scandinavian award for what he did, but he basically created the idea. There's a really nice textbook that he wrote, or it's not really a textbook, but it's a book about nanotechnology using DNA. So there's lots of interesting things that you can do. Part of this aside is that how do you study these things? Seeing it is one thing, turning it in machines. One of the things that Ned was really interested in was using DNA to make machines. Okay, we have machines in our bodies. That's myosin and that's actin, those kinesins, those are kinds of machines that we talk about. The replication fork is a machine. Okay, and so Ned was thinking about this as from the perspective of other kinds of machines. Too many thoughts in my head. There was a prize given in the 50s, I think. A physicist asked the field, can you use molecules to make a machine and prove to me that it actually is acting like a machine, like a farm instrument, implement or farm equipment? And somebody did it in like 6 months. Okay, so it was easy to do, although I think we have far better resolution today than we did back when. Okay, so we're going to take a short break. And then we're going to talk a little bit about where we are with problem sets. And I don't want any of you to go away, actually, because I'm not, it's quite clear that a lot of you are working really hard. I'm not saying that all of you aren't working really hard. And you're all having different challenges as we go through this, okay? That is the purpose. I'm doing that on purpose, okay? I like to say, I don't always mean it, but I like to say, I want to make you cry. Okay, see, you're smiling, so that's good. I want to make you cry because I want you to appreciate that this is not easy. Okay, this is not something you
Dr.
just.
Korea, this is not easy.
And believe me, I know that. Okay, this course is based upon a course that I took when I was a first or second year graduate student. It might have been first year graduate student. Yeah, it might have been second. I can't remember exactly. The 70s are a long time ago. That was 2 semesters long.
Okay.
Used multiple books, some of which I still own and I still use. 2 of them are open on my desk right here because I tend to refer to them and read them. I'm actually writing a manuscript or 2, and I'm using stuff in these books. And it was the same idea. And the way Dave Yafantis is the guy who taught this course at University of Connecticut, go UConn. The way he taught this course was problem sets. He would give us problem sets and he would give us the weekend and then we would turn them in. Okay. And then we would go over them usually.
I agree with you that if you had not given us this problem sets, I don't think we'd be getting the concept. Like we'd understand when you were teaching and read the material, but doing problems really helps you understand.
Right. And I think that's the point.
Yeah.
Okay. And I think you get caught up in the numerics of it, in the mathematics of it, but it's really getting sort of the concepts and applying the concepts where you really begin to understand. The thing that I want you to really understand and appreciate, there was a small rebellion when I was a graduate student, and we started complaining to the faculty that they weren't teaching us enough.
Mm.
And the reason was that, yeah, they were teaching us stuff, but we actually needed to know things a whole lot better and in a whole lot more depth than what they were teaching us. Okay. And we started, and our response was to start our own journal club. And the students just met once a week and went over papers, because you taught me X, but I actually need to know X, Y, and Z to do this experiment and interpret this data. And they were like, well, that's for you to figure out. Go figure it out. Okay. And so I think that that's part of the issue here, that it's an introduction to these concepts. It's not by any means, shape, or form the endpoint. And that is part of the criticism that I get from a lot of the things that I do, that I try to incorporate too much into some of these lectures, and too many ideas, too many papers as reading. Well, the truth of the matter is that there are 10 times more papers that I really want you to read to understand this stuff. And I think that's sort of the issue. I've said this to you before. You know what's in textbooks. Do you appreciate that everything in a textbook came from a paper? It actually came from 10 papers, or it came from 100 papers. And that textbooks summarize and distort and misrepresent and don't really teach you what you need to know. You've never heard of ZDNA. That's crazy. There's I bet you there are 1,000 papers on ZDNA. And it's fallen out of favor. Does that mean that ZDNA isn't important, or isn't curious, or isn't informative? That's to be judged, to be determined. Okay. So that's sort of what this challenge is about. All right. And so what I'm going to do is not answer your questions. You're going to answer your questions. So we're going to go all the way back. I think problem set 1, assignment 1 was the one out of Siegel. And for the most part, everybody did well. Okay. Some of you probably still owe me sort of an improvement to get a higher grade. Problem set 2, I think everybody did well in. Problem set 3 was the disaster of error propagation. Okay. And some of you still need to sort of turn some stuff in. So what we need to do is sort of go back to old assignments and figure out what needs to be sort of clarified and looked at, if anything. But I'm not going to answer. One of you is going to answer, because one of you got it right. Some of you got it right. A lot of you got it right. All of you got it right. And maybe we don't have to talk about that problem. But then you answer that question. Okay. And then we'll move forward, and we won't get very far. We won't get up to 5 and 6. And some of you have not turned in 5 or 6 yet. And I know some of you are working on 6 and 7 now. Okay. And then maybe we'll add this as something we do every week. We may have to do this in another time. And that's something that you'll have to tell me you want to do and when you want to do it. But we will go over some of these problems together. Okay. But again, I don't really want to do all the talking. I don't want to do any of the talking. Okay. I want you to answer the questions. Okay. And if we can't do it, then we need to do another session where you can. Okay. I was screaming at the television last night when UConn was starting to lose to North Carolina State. And what I kept saying was, somebody needs to step up. And then in overtime, one of their players stepped up and scored 15 points, and they won the game. So I'm saying, who's going to step up? So let's take a 5-minute break. Okay. And we'll go back to assignment. Maybe we'll go all the way back to 1, and we'll look at it and then decide what we're going to cover. Okay. So 5 minutes.
Hey, Dr. Correa.
Yeah,
I don't think any of us mentioned it, but we have to meet with Dr. Grange at 12.
yeah,
In the
yeah.
grad school,
We'll
just to-
we'll stop before then because I appreciate that.
Yes, sir. I just realized nobody said anything. It's on our email.
That's okay. So let's see what I'm looking at here. Okay, so the first assignment was all Siegel, as I said. And I think everybody, for the most part, turned all of those questions in. I think some of you had some, there was one aspect or something that had to be, I think it was on a molecule basis or something, but basically most of you had that in, and I don't know that there's anything there for us to talk about. What was number two? Number two was, oh, the PCR question that was talking about, and then deriving the equation in good. Okay. Okay, and that's something that I think everybody was able to do. And so the point of that was teaching you about buffers and temperature dependence of PKs, et cetera, which was actually an introduction to thermodynamics if you didn't appreciate it. So number three is,
Number three, we discussed before. You gave us hint. We all did it wrong, and you kind of said how.
right, and a lot of
The
you got
derivation.
all of that. Or at least I know we discussed it. I'm not sure that
Yeah.
everybody is really up to snuff on it is part of the issue. So is there anything about, so where would I find that? That was,
It had derivation.
okay, so the majority of it was this particular assignment right here.
Yeah, yeah.
Okay, and so it really had to do with the A, B, C, D part of this assignment.
Yeah.
Okay, and so is there something that somebody wants to discuss at this point, or do you want to not discuss it? Because I think a couple of you haven't turned everything in yet.
I am good with this part. Oh, will
Okay,
you
so Jelena is
explain?
good.
Yeah.
How about the rest of you?
I'm good with the past two.
Nobody?
Mm,
I'm good with that too.
So the formula is this basic idea up above at the top. I'm not, two of you have spoken up, but not everybody. It has to do with the fact that the error can be expressed as the error in the dependent or independent variable squared times the partial of x with respect to u squared plus the error squared in the other variable v plus the sorry, I'm making this a little bit bigger. There. That's bigger. And this is, and then we generally ignore the cross terms, the covariant terms, partially because they cancel, partially because we often don't know what they are. Okay. And then it gives some of the formulas that are derived in the chapter. Maybe the most important one is this logarithm term, where the partial of ln x with respect to x is 1 over x, or in this case, plus and minus bu, so it's 1 over u. Okay, and the b is actually gone because the natural logarithm of bu is the natural logarithm of b plus the natural logarithm of u, and so that term cancels. Okay.
Yeah.
All right, and so it's the application of this, and the problem has been taking derivatives.
Yeah, that's where I struggled. The derivatives and all, but I think now doing this, I'm a little bit clear. I know at least how to do basic derivatives. Yeah.
Okay. All right. So let's say this, because nobody else is speaking up. If you're still having trouble with this, you need to talk to me in some way, redo it in some way, do enough of it so that you actually learn it. And part of this is that you've thrown away some points. Okay, because not all of you have turned in the remake of this, the redo of this. And the reason for that is I'm guessing that you still didn't overcome what you're talking about. Okay. And recall that first and second one. I make you I have to go back. Sorry. The one that is 1/2 u plus v. So is that correct? I think I asked you to solve it. I asked you to solve it as though it was 1 over 2 u plus v.
U plus v.
And some of you did it both ways. Okay. And so this is the error in x squared is equal to the error in u squared, the partial of x with respect to u squared, plus the error in v squared, the partial of x with respect to v squared. Okay, and written this way, this answer right here, okay, is 1/2. And this answer here is 1/2 because the partial of u over 2 is 1 over 2. The partial u to the first power is u to the 0th power. And so this is what you end up with. And it's squared. So you end up with 1/4 times u squared plus v squared. And that's the answer.
Yeah.
Okay. And then this one's more complicated. I won't go through it. And so that's the main emphasis that you have to go through for that one. Okay. In the ones that you have to rearrange, the rearrangement is expressed in what the final answers are, because certain sorts of arrangements, the product or the quotient, gives you a simpler answer, the sum of the squares. And then what ends up happening is they end up dividing by x squared or u squared or v squared to make this simpler, so that the traditional answer ends up being, if you have, come on, if you have u, stop, if you have u times v, for example, then the error, I'm not sure what I need to turn on or off here. The error, stop. There's something I'm not doing right up here. The error in x is the square root of the sum of the squares of the relative errors.
Square plus.
And so that's the thing that you end up dividing by x squared or u squared or v squared, and you ended up doing this all the way across, and things canceled out to give you this. And so this ends up being the algebra that you have to do to come up with that final answer. And the weird thing is that u over v gives you exactly the same answer. Exactly the same answer, as you can see here. This answer and this answer are exactly the same, whether it's the quotient or the product. They reduce to exactly the same term. The difference is this -2, and we neglect that term in the covariance. So you get exactly the same answer here and here.
So did you say the product of u and v and u by v gives the
Yes.
same answer?
In terms of the error propagation, yes.
Okay.
Yes. And so that was the algebra that you had to go through, because when you get the answer in these units, you then divide by x to get the relative error. This is the relative error squared. This is the error squared, and this is the relative error, because you're putting the error on top of x as opposed to the absolute error. And so if you divide through by x squared, then what you're doing is you're dividing through by uv squared, because x is equal to uv if you're doing this one. And that's where you get the u in the denominator here and the v in the denominator here. Okay, and so it expresses it in terms of relative errors. And the relative error is often easier to think of. If I tell you the error is 1%, that's the relative error. But that 1% could be 0.0001 in absolute terms, or it could be 10 in absolute terms. Okay, and so knowing it in percentage is often informative. Okay. All right, so if you're somebody who needs to review that, say yes, and it'll save something. Close that, close all tabs. Okay, so that was that. And then I had given you one that involved the logarithm. Okay, as part of that. That was 3. Yeah.
Yeah.
Okay. So this one down below is one that a lot of people had trouble with, and this had to do with the algebra. And I gave you a PowerPoint that addressed this, taking the derivative with respect to R, and then solving for R, setting it equal to 0 and solving for R. In this particular case, you don't need to really know, you don't need to take a second derivative. You don't really need to know. It's obvious that it's a minima. It's just really the rearrangement. When you take the derivative of R to the -6, then you have to plug in 6 divided by R to the -7 and 12 divided by R to the -13 and then rearrange. So I gave you a PowerPoint that sort of went over that, a one-page PowerPoint. This was a simple propagation of the reaction, and it ended up being the difference between the pKs. And this one had to do with the projection of the OH bonds onto a common axis. And a lot of you solved it in a different way than I would solve it, but I think I also gave you a PowerPoint for that. Am I not correct about all of that? So what is there something that we need to do here?
I was a little confused about the percentage ionic character. I had to look up online to know what that really is for that question.
So which question is it? I'm sorry.
Number one, when we have to find what fraction of this total is measured value, the percentage ionic character, I didn't know much about that particular questions. I didn't know what percent ionic character was when I read that question. So if you could clear out a little bit, even though I got the answer right, I wanted to be more clear.
So in the chapter 4, by Creighton, which was one of the readings, this problem actually comes out of Creighton. I probably stole this from Creighton in the 90s. This is where I got this question. Okay. And it has to do with the fact no. Oh, pen. There we go. Pen. It has to do with the fact that water is H2O, and so each of these are a bond. Okay. And quantum mechanically, this is a covalent bond, but it's not entirely a covalent bond. It has some covalent character. So quantum mechanically, it has something to do with the orbitals of the electrons around the oxygen and the protons. And they're making bonds. Okay. And so these are probably s orbitals that are primarily in the hydrogen. That is making this interaction. Okay. So this is the quantum mechanical definition of the first orbital, which has to do with the numbers of electrons. All right. But the interaction is not entirely covalent, because this molecule and these molecules have electronic character. So there's partially an excess of electric charge on the oxygen and on the protons. And so part of the bonding that is going on between this oxygen and this proton is actually ionic. There's actually an attraction between this negative charge, excess negative charge, and this positive charge. This has to do with what we refer to as polarizability, and the fact that oxygen can be polarized in a way that it could have a dispersion of charge. And so we talk about this often when we talk about double bond character, okay? And the fact that excess charge can be put into other places. So if this had a carbon-carbon bond, some of this double double bond character can move around. Okay, and it sets up an environment where this has, I think I'm writing it this way, this has ionic characteristics to it. And so there's some charge-charge interaction that's going on here. And to do this, you can actually turn these electrons into movable groups that can move into other bonding. And this is what creates the double bond character in a peptide bond, for example. And so that's what this question is trying to get at. Given the dipole moment of 1.84 dBi, which measures something about the charge separation, it's 0.957 angstrom, so it's approximately 1 angstrom long. What fraction of the interaction must be covalent and what fraction of the interaction must be ionic? And that's the measurement you ended up having to make. Okay, and so knowing what the charge-charge separation was is what allowed you to convert this 1.84 into a certain amount of charge-charge interactions, as opposed to what it would be if it was entirely covalent with no ionic interactions. And what you ended up having to do was project this onto this direction, because it's, the dBi is measuring the dipole moment, the average dipole moment in the molecule. And a dipole moment usually runs from negative to positive. So it's the direction is this way, and you're projecting this axis and this axis onto this bond. Some of you did it a little differently than I do it. I do it by solving for what fraction of 100% this is, and then projecting that and then summing it by 2.
Okay.
Okay, and that's the way that I did it. But it's this ability to have this charge separation, the ability for oxygen to be polarizable and hold on to excess electrons. So this attraction is partially ionic.
Okay.
Now, I'm not going back through all of the question. Do you have your problem set? Do you want to explain this, or do we need to do more of this? I think in the end, most of you ended up getting this. Most of the problems in this problem set had to do with this derivative down below. And as I say, I gave you I don't remember where I put that. I gave you a PowerPoint where I solved that problem. Where did I put that?
Yeah, you had said it, send it to us.
Equations of state, exact differentials, divide A2. Substitute equation of state. Right, and so this was what I sent to you. Okay, and I'm showing you that there's a charge separation. If it's 1.957, it's Z times D. The units for the dipole is 1 charge separation at 1 angstrom. So 4.8 dBi, so it's 0.957 times 4.8 gives the fraction of protons that are separated. And then you have to project it cosine times this difference and then divide 1.84 divided by that sum.
I don't think you send this to us.
I didn't?
I don't think so. Have you uploaded this on the Canvas? Or
I thought I sent this by email. But I can
I-
upload this because this had the equations of state.
I don't remember you sending us this, to be honest. Yeah.
Perfect differential. And then this was the one that I sent you that has to do with taking the derivatives and rearranging.
I remember this slide, but not the one.
All right, I'll put this up on Canvas.
Okay.
This belongs in
4.
problems. Yeah, so maybe in lecture 4, I'll go put it out there. I'm not sure.
Okay, that'd be great. Yeah.
So I think that came up in hydrophobicity,
Yeah.
chapter 4. Insert a document. And I think I just found that here, yeah?
Yeah. Introduction to
Equation of state,
frequency state.
submit.
Yeah. Thank you. Thank you.
Okay, and then down here, I'll say save. Okay, so that will have the water, that will have the Leonard Jones potential, and that will have something about perfect differentials. Anyone else?
If we're going to assignment 5, the one I struggled most was to find the K-app, the derivation of the K-app. I've sent you the one that I did last time, but I don't know how. Yeah. What's that assignment?
Okay, so which one?
Where we had to derive the K-app, which is equal to KNI by 1 by pepstatin, the derivation from the book. 2.1, I don't see that here.
So is this lecture 5, do we think?
Yeah, it should be, because it was assignment 5, so it should be lecture.
This 5, 2.5?
Yeah.
It may have actually been problem 2.10.
2.10.
Oh, so this is the down at potential. So it's not this one, it's the other one.
No, it's the, yeah, it's the, it was the 2.1 equation from the book, and you wanted us to derive that. You put that on the PowerPoint slide too.
Right.
Yeah.
Oh, you mean
To find the K-app apparent displacement.
this question? And so this continues to
Yeah,
be a
yeah.
question that you're all struggling with, yes?
Yeah.
Okay.
Definitely.
And I keep wanting to avoid doing it for you. And I thought I created a PowerPoint for this as well. So let me go back here.
It
You
did.
did.
Oh, maybe it's there.
That helped a
It's
little bit.
derive equation A2,
There it
I
is.
think.
Yeah.
Yeah.
Yeah, that it helped a lot, but still
Hmm.
not finished.
So this is deriving these equations and this is deriving this equation. But I think I was thinking about this the other day. So part of what's going on here, if you read the way he writes it, okay, the way he writes it is use the thermodynamic cycle. Go back and look at the way he expresses it. Use the cycle. Okay, and what he means by that is this pathway is binding of the AC. Okay, and so that's this equilibrium constant here. This pathway is displacement. Okay, and so this is a displacement reaction where the K and I kicks off the AC and it gives you a negative enthalpy. But at the same time, the AC is going off, binding is positive, and so this gives you a negative enthalpy, and this going off contributes a negative enthalpy as well. So you're getting both heats here at the same time. Okay, and that's this displacement here. So what's happening here is that this first step, and I think I have that back here, this first step involves this binding to the open site. This second step involves this, the K and I binding, and the AC coming off. Okay, and so another way of writing this second step is that it's KNI plus what I'm writing down as HIV is making a bond. Well, I write it different ways every time I do it, don't I? But at the same time, let's do it this way. I'm sorry. HIV AC comes off. So this is the sum of two steps. Okay. So this path going from here through here to this final state involves this reaction, this reaction, this reaction, and this reaction. Okay. This pathway over here, thermodynamically, is equivalent to these three other steps that are going on, because this is a cycle, a thermodynamic cycle. And so this pathway involves two steps. It's actually three reactions, because first the AC binds, and then the KNI binds, but in the process, the AC gets kicked off. Okay. And so this one step, if this is a thermodynamic cycle, is the equivalent of everything going on here and must be equal to everything going on here. And that's where this K apparent comes from. And that's why it involves this other set of parameters. And so that's what he's trying to get you to do, to see that somehow this pathway gives this result. And it's the thermodynamic cycle character of it that is important. When we emphasize this, and so I know that I'm taking an aside here, But when we talk about this in terms of oxygen binding or dimerization, in the fact that dimerization and oxygen binding are two of the steps along the pathway to oxygenating hemoglobin, that you can use the dimerization as insight into oxygen, and you can use oxygen binding as insight into dimerization. Likewise here, the information that you have from this pathway is equivalent to the information that you have from this pathway. And that's sort of the trick. I meant for this slide to provide that to you when I did this, but I don't think I went far enough in explaining it to you. So I know we're running out of time now. You have
Yeah,
a meeting
yeah.
with Dr. Granger. Let's stop with this and come back to it. Okay.
Yeah, thank you so much, Dr. Correa.
And so what you need to do, I'm going to say keep. What you need to do is give me some feedback about what we've been doing.
Okay.
Okay. And then we'll pick up, I guess, next Tuesday. But I intend that we do a little bit more now and that we set up a time to do more problems in a discussion the next time we meet.
Yeah,
Okay.
and this will be really helpful. Yeah, discussing question and all.
All right.
so-
And so we know we're meeting Tuesday. We know we're doing electrophoresis. I've already got an outline of a PowerPoint ready to go. I don't have it yet posted yet, but I have stuff posted out there for you to read. Okay.
I will be at EB conference next Tuesday, so I will log in for sure, but I might not be.
So what day are you back from?
I will be back Tuesday afternoon.
Are you the only one going?
No, me,
No,
I think
I'm also
Douglas,
going.
yeah, Douglas and me.
Okay. Well, logging in, or you will also have access to the
Yeah, yeah,
MP4.
yeah.
Okay. And so maybe we should then try to set up something for later in the week. You meet with John on Thursdays. We could do it Thursday afternoon. We could do it Friday. Let's talk about that. Okay.
Okay.
And we'll decide on a time to meet next Tuesday, but you guys should be involved in that decision.
Okay.
Okay. So are we going to do it Friday morning? We're going to do it Friday afternoon. When are we going to do it?
Okay.
Okay.
Yeah.
All right.
Thank you. Bye.
Bye.
That's Dr. Correa.
Yeah.